All right. Thank you, everyone, for coming. This is, I believe, the last talk for the day, so I'll try to keep it short. So today I'll be talking about how can physics inform deep learning methods in scientific problems, which is very much related to the theme of this workshop. Here is an outline for the talk for today. We'll first try to understand why do we even need physics to inform deep learning methods. Why are black box methods not sufficient just by themselves in scientific problems? I'll discuss this emerging paradigm of theory-guided data science that tries to integrate scientific knowledge with data science methods. And in this paradigm, I'll discuss some of our recent work on integrating scientific knowledge with deep learning methods. And finally, I'll talk about some of the future research directions in this area. So we are all aware of the deluge of big data in physical and life sciences, which is reflected in all the great talks that we heard today. We have data from satellites, from models in climate science, in particle physics, in quantum chemistry, quantum physics, and so on. All of this data makes it possible for us to apply recent advances in data science, such as deep learning, to extract knowledge, patterns and models automatically from large volumes of data. And these methods are generally developed and deployed in a manner that is agnostic to the underlying scientific principles driving these variables, thus earning the name black box models. These methods have been hugely successful in commercial problems in computer vision, speech, language translation, and so on. And we have been hearing this throughout the conference. And there is a huge anticipation and growing promise in the scientific community to untap the power of deep learning for scientific problems. This is reflected in a series of special issues in Nature and Science journals. To the extent that some have even referred to the rise of black box data science as the end of theory, where the idea is that given large collections of data, we can completely discard scientific theory-based models that have been the cornerstones of scientific progress and completely rely on the information contained in data. However, such tall claims generally fall flat when black box methods are actually applied in practice in scientific problems. And a case in point is the rise and fall of Google flu trends. So this was a system to predict the onset of flu just based on Google search queries without using any physical knowledge of how diseases spread. And despite its initial success in the years that was used to train the model, it soon started overestimating by several factors to the point that it was eventually pulled down. And this is not an isolated story. There are many articles and reports that highlight the pitfalls in black box applications of data science in scientific problems. So what's so special about scientific problems that makes black box methods fail, or at least not able to achieve similar levels of success? Well, there can be many reasons. One of the primary reasons is that in many scientific problems, we are dealing with a large number of variables that interact in complex, non-stationary ways, and we often have limited number of samples. For example, in climate science, even if we look at coarse resolution data sets, we have about 10,000 locations or variables across the world. And we only have data, good quality data for the last 30 to 40 years, which is starting from the satellite era. Or we may go to maybe 100 or 150 years. This makes it difficult to train data-hungry methods to achieve good training performance. And even more so, when the size of both the training and test sets are small, even standard methods for evaluating model for performance break down. This is because if we have a limited labeled set, howsoever we may divide or split the data into training and test portions, it is easy to learn relationships that look good on both the training and test sets, but do not hold well outside the labeled set. This is what actually happened with the Google flu example. And a more fundamental concern with black box methods is the need for interpretability in scientific problems. Yesterday we had a great symposium on interpretability in machine learning and a very lively debate. And I believe interpretability is even more important in scientific problems for several reasons, because a method, a model that can be explained by scientific theories, by existing scientific theories, can form as the basis of scientific advancements. It can be used as building blocks by other researchers. And a more direct importance is that a model that can be explained by existing scientific theories stands a better chance at learning generalizable patterns and avoiding the phenomena of overfitting. So with that understanding, let's look at this dichotomy between theory-based models and data science models using this 2D view. On the x-axis, we have the amount of data that we are using, and on the y-axis, we have the amount of scientific theory that we may be using. And in this space, theory-based models would reside in this particular region where they make ample use of scientific theories that can range from closed form equations to numerical models of dynamical systems. And despite their huge progress, they contain knowledge gaps in describing certain processes that are either too complex to understand or are too difficult to observe directly. On the other side of the spectrum, we have data science models that make ample use of data but are agnostic to the underlying scientific theories. And they both make ineffective use of the two sources of knowledge, scientific theory and data. And there is a promise there is a need in developing methods that can use scientific theory and data science at an equal footing. This is the paradigm of theory-guided data science that tries to take full advantage of the unique ability of data science methods to automatically extract knowledge and pattern from data, but without ignoring the treasure of knowledge accumulated in scientific theories. Our recent perspective article on this topic tries to build the foundations of this paradigm by discussing several ways scientific knowledge can be integrated with data science methods in various scientific disciplines. And this idea of combining scientific knowledge with data science is already beginning to show promise in a number of emerging applications. And this is also reflected in all of the talks that we heard today, which are all examples of this line of research. Here is just a short highlight of some of these works. This is in no way complete or exhaustive. We have some of our own work in earth science that I'll be going through today. There are approaches to build machine learning methods for turbulence modeling, for discovery of novel materials, for new density functionals, and in many other domains. And there are many other conferences and industry initiatives that are also focusing on this line of research. One of the examples is the physics-informed machine learning workshop at Los Alamos National Laboratory. So let's try to understand what theory-guided data science is. Let's look at one of the overarching objectives, which is to learn physically consistent models. Traditionally, there is a notion to favor simpler models to achieve generalizability. And one way to view this is by looking at the space of all possible models for a given predictive learning problem. Where the star represents the true nature of relationships, the true model between the input and output variables. And we have three different families of models, M1 to M3, ranging with different levels of model complexity, shown as these three curves. Any point on these curves represents a specific model that can be learned given a specific sample of training instances. So what we can see is that models belonging to M1 on an average are quite far away from the truth, so they have a high bias. But they do not vary a lot with small changes in the training set, so they have low variance. On the other hand, models belonging to M3 on an average are quite close to the true model, but they have high variance. So we need to reduce both the bias and the variance, and one way to look at this is to say that any estimate of generalization performance has to depend not only on the training accuracy but also on the model complexity. So we want to be as close to the true model as possible without having a lot of variance. And this is at the heart of several machine learning algorithms that try to use different notions of model complexity rooted in statistical principles. But in scientific problems, there is another source of knowledge that can be used to make this trade-off, which is the physical consistency of the model. So the basic idea is that if we can prune spaces of models that are inconsistent with our available scientific knowledge, we can reduce the variance without likely affecting the bias. So this would result in a revised notion of generalization performance that depends not only on the accuracy and the model complexity, but also on the physical consistency of the model. So this is at a very high level what the goal of physics-guided neural networks or theory-guided data science is. And what I'll talk about next is a specific framework for learning physically consistent neural networks, which is physics-guided neural networks. This is a work that is in submission at SDM, and a preprint of this work is available on arXiv. To illustrate this framework of PGNN, let's look at an example problem of lake temperature modeling. So in this problem, the basic goal is, given a list of input drivers, such as the amount of radiation, air temperature, and so on, we want to model the temperature of water at every depth in a given lake across time. So this is looking at a 1D modeling of temperature over time. And the basic approach is to use a physics-based model. So the state-of-the-art physics-based model is a general lake model, GLM, and just like many other physics-based models, it involves parameters that have to be calibrated individually for every lake, and this really improves the performance of the model. For example, for a given example lake in Minnesota, if we use the uncalibrated model, which uses generic parameters that haven't been tuned for this specific lake, but work reasonably well over a majority of lakes, we have an RMSE in the model predictions as 2.57 degrees Celsius. But if we use the labeled data for this particular lake to fine-tune the model, we can achieve an RMSE of 1.26 degrees Celsius. But this comes at a cost of the amount of data, the labeled data that we need for calibration, and many of these calibration methods are computationally expensive. So the hope is, can we use machine learning to help in this process, to achieve better performance with limited training sizes and with limited computational resources. And one naive solution could be to train a black box model that takes us from the input drivers directly to the target output without using any physical knowledge. But in the presence of physical knowledge, we can do more. And the first and the most simple way of using physical knowledge is to use the output of a physics-based model as an input in a neural network. So along with the input drivers, we can also use the outputs of a physics-based model in the input layer of a neural network, and we can have multiple of these hidden layers fully connected to finally give us the estimate of the temperature y hat on the output layer. This is in some sense trying to build hybrid physics data models, where we are trying to see if a neural network architecture can estimate the residuals of the physics-based model using the feature space of the input drivers. And the traditional approach to train any such neural network would be to minimize loss functions that depend on let's say the discrepancy of the model predictions and the actual observations, as well as on L1, L2 statistical norms of model complexity. But apart from these two losses, we can also use loss functions that measure the consistency of the model with respect to physical principles. So the basic idea is, any model that makes estimates of temperature should be aware that temperature is related to many other physical variables through these physical relationships. For example, temperature is directly related to the density of water through this nonlinear physical relationship, where water has maximum density at 4 degrees Celsius, excluding the salinity of water. and the density tapers off as we move away from 4 degrees Celsius. So any estimate of temperature can be converted using this physical relationship to an estimate of density, rho hat. And once we have these estimates, we can exploit a key physical constraint between the density and the depth of water, which is that denser water goes down to the bottom of the lake and thus is at a higher depth. So if we increase the depth of water, we would see that the density would monotonically increase. And this simple physical relationship can be used to design a physics-based loss function as follows. For any 2 consecutive depth values, we can look at the difference in the density estimates at those 2 depth values, shown here as delta I, and this delta I has to be greater than or equal to 0. So delta I is basically representing the violation of the model predictions with respect to this physical constraint. And a very simple loss function could be just to look at the sum of all physical violations that the model is making. So this would lead to the following estimate of loss function, where along with the training loss and L1, L2 norms, we are also using a physics-based loss function with a proper hyperparameter along with it. So this is in some sense a working implementation of the high-level goal of introducing physical consistency in data science methods. And a good part about this is that it doesn't require labels. It can be applied in an unsupervised fashion. Here are the results of this model. So we already looked at the RMSE of the uncalibrated model, which is 2.57 degrees Celsius. If we instead apply a black box neural network, we can achieve an RMSE of 1.77, which is somewhat better. But if we combine both of them and use physics-based loss function, we can achieve an RMSE that is better than both of them. It is even better than the most finely tuned calibrated GLM model. So this demonstrates that physical consistency can ensure generalizability. And another advantage with this is that it can produce results that are physically meaningful. To show you that, here are the density profiles of 4 different models on this particular lake for a given time. The blue curve shows you the density profile for the uncalibrated model. The red curve shows you the density estimate of the calibrated model. And you can see that there is this bias in the uncalibrated model, which is the horizontal shift. If we use a black box neural network, it is able to rectify this bias, but it produces physically inconsistent solutions, because the density first increases as we increase the depth, but then it starts decreasing. So it's not physically meaningful. On the other hand, the black curve shows the PGNN framework, which is able to rectify the bias as well as capture more variations than captured by the red curve, which almost goes flat in the upper and lower portions of the lake. And it's able to do this while being physically consistent. And this is just for one single time step, but we can look at many other time steps where similar results would show up. So this work is part of a bigger goal of theory-guided data science, and there are several future research directions that need to be explored. We already talked about ways to use physics to guide the learning of data science models using loss functions, but there are many other approaches. We heard about the use of pivot constraints, which is another example of theory-guided learning. Theory can also be used in the design of the data science model by choosing right response functions, activations functions, like the jet parts trees that was introduced in the morning. Theory can also be used to refine the outputs, to post-process and to prune the results. There is another emerging direction to create hybrid models of physics-based models and data science models, so that data science can augment or replace components of physics-based models that suffer from high systematic errors. And finally, there is this long-standing tradition of inference of model parameters where data science can help. And there are several posters and presentations that talked about this work. So with that, I would like to conclude. So we introduced, we discussed the paradigm of theory-guided data science, which is gaining prominence in several scientific disciplines. And thank you. Please let me know if you have any questions.
Thank you. So we have time for one question.
Okay, neural nets are very good at interpolating, but what about extrapolating to a region outside the area where it has been trained? So how do you know that the neural net is not extrapolating and results have been controlled?
So the question is, how do we know that the model is not extrapolating and interpolating? Well, if we are working in regions regions of feature space where we do not have samples, we can look at not just the predictions, but also how confident are the model predictions in those feature spaces. And if we do not have samples, the confidence should be low. So I think combining model predictions with the confidence scores is one way to look at that.
Great, thank you.